In the last session, we were discussing about simple linear regression, wherein we had one independent feature called X and one dependent feature called Y. And because these two variables are having a linear relationship, we were able to find a model which could represent a linear equation of this form. So the agenda was to find out the beta 1 value and beta naught, and of course we had to find out the hypothesis testing to find if the model was significant enough and the sigma and the slope was significant or not. So based on this, we were able to figure out the y hat, and we were eventually reached out to a point of finding the line of best fit. Say line of best fit. This line of best fit was the one which was having least sum of squared errors. Okay, which is nothing but y minus y hat square. So whichever model was having the lowest sum of squared errors was the one which was chosen to be the line of best fit. Now, what would happen when there are more than one independent feature? Say, for example, instead of having just X, what is the way to deal with when we have more than one independent feature? So let us say that I have X1, X2, and X3, and then we have our target column Y. So this is what the data frame was looking like. Even in this case, previously we were talking about just a line. In this case, we would be talking about a hyperplane. Now this is a hyperplane which would be a three-dimensional axis, for example. As the number of dimension increase, it would become more and more difficult for us to visualize the data. But nevertheless, as long as we keep the data, as long as we keep the model to be linear, it would have the same assumptions of what we discussed in the last class. So what I say by linear is that, let us say, when we have beta 1 x1, this is a linear relationship. If it is beta 1 x1 to the power of 2, this is polynomial relationship to the degree of 2. Similarly, if it is beta 1 x1 to the power of 3, it is polynomial relationship to the degree of 3, and so on. But because we are talking about linear regression and we assume that the data is having some linear relationship, only then we are going to build a linear model. So what we would have to do is, instead of having a model which was showing as beta 1 x plus beta naught, we would be coming up with beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta naught. So this, whichever, how the based on the number of dimensions that we have, that many betas we will have to figure out. Okay, so as we keep increasing the dimension, the linear model should also be trying to consume all the independent features. Okay, same like how we did for the previous session, we would also be trying to evaluate what is the plane of best fit. In the last session, we discussed about line of best fit. I think you remember this slide, wherein we tried to find out which model is good, because all the models are passing through most of the data points. So what we discussed, we need to find a model where y minus y hat to the power of 2 should be as low as possible. This is called as sum of squared errors. So the sum of squared errors should be as low as possible. So when we are trying to find a plane of best fit, previously it was line of best fit. So imagine that each line is now a hyperplane. Now hyperplane can be in any angle towards, you can imagine how the hyperplane would look like. So how to achieve this hyperplane? Let us say that we have three dimensions, maybe not three. Let us say that we have three independent features. When I say independent features, it is X, and one dependent feature, which is Y. Okay. Let us not talk about causation. Let us say that all these are independent and only one dependent variable is there, that is called Y. So how to come up with this beta 1 x1, beta 2 x2, and beta 3 x3? So there are a couple of ways. One simplest way is to do a forward selection. Now what I'll do, I will create a model. I'll create a model y hat with just one feature. It could be any feature that we have. And let us say that I have this feature model. Now this model is having some sum of squared errors. Let us say it is having like 150, for example, on a given data set. Now I'll try to add one more feature to it by doing this. Now instead of converting just inverse, instead of considering just x1, I will now be considering both x1 and x2, and then I'll build one more model. Now this is my new model. For my new model, again, I'm going to calculate what is my SSE. Let us say in this case, the SSE is 125. So you keep on adding new independent features until you reach to a point where the SSE is lowest. So you'll try to find a sweet combination of those independent features where the SSE is as low as possible. This is one way where you keep on adding. Okay, if let us say for when you added x2, instead of SSE as 125, maybe you got 170. So in this case, because you by adding x2 the errors are increasing, you will remove x2. Okay, and then you'll try with x3. So if x1 x3 combination is much better, then you'll stick to the model which is x1 and x3, and probably it is having a lower SSE. So you have to find a sweet spot where the sum of squared errors is low. So this is called a stepwise selection, and the stepwise selection can be forward selection or it can be a backward elimination. The backward elimination is a process where you try to remove the variables. Instead of adding it, you remove. So what is the start of point? You try to build a model by considering all the independent features. Beta I xi plus beta naught. By considering all the independent features, and then you try to remove one feature from the last. So once you find a model which is having the lowest SSE, probably that is the best model. Okay, and there are a couple of things that we might face when we build a multiple linear regression model. Okay, I'll discuss about that in a bit, but how to conclude about line of best fit, or how to conclude upon which combination of features is good. So there are a couple of ways that we can look at. The first thing what we can look at is Akaike's information criterion. So there is something called as Akaike's information criterion, which will help us identify which feature is good for the model or which feature is not good for the model. So when you are doing a stepwise selection, we can go and calculate this value. This is called as Akaike's information criterion, which is which is indirectly dependent on the sum of squared errors. So for each combination, you would be finding out the sum of squared errors, and then you would be coming up with one model which is having least AIC value. Whichever model is having the least AIC value is the best model. Okay. So again, you don't have to go dive deep and look into all the formulas. We have libraries to do this. So you don't have to worry, even if you do not understand what this formula is doing and all, we don't have to worry. All that is needed is, given a case where you have n dimensions or n independent features, and you are wondering like how to analyze which combination of these features can give us a best model, is found out by using something called as Akaike's information criterion, if you're going with a stepwise selection. Let us say you don't want to go with stepwise selection. Well, far and good, no worries. We can apply many different techniques. We'll reach to the point when we discuss about techniques. I'll tell you about that. But for now, if you want to go with a stepwise selection, you have to use something called as Akaike's information and choose a model which is having the lowest AIC value. Okay, this is one way. But there is a problem. Now, what's the problem? As we keep increasing our independent features, there might be a possibility that a independent feature is affecting one more independent feature, or a combination of independent features a combination of independent features is affecting one more independent feature. We discussed this. This is called as correlation. Sorry for that. This is called as correlation. So what is correlation? If you remember the correlation, we had values like -1 to +1, and covariance was -infinity to +infinity. If two features are having a relationship, there would be a very high covariance, and the value of correlation is either towards +1 or towards -1. This is about two features. Now, what if the independent features were having this? So when two or more independent features are having a relationship amongst them, that is termed as multicollinear. It means that when you have independent features, when I say independent, all of these should be mutually exclusive. Say, for example, this is my temperature. This is my, let us say, my age. And maybe this is whether it was raining or dry. All of them should be independent. Now, on the other hand, if I have features like x1, x2, and x3, and x2 is nothing but 2 times x1. So when I change my x1, my x2 would become 2, and x3 might have some other feature. When my x2 is 4, my x1 becomes 2. So these are very highly correlated. Just by changing one, if I do not see any change in any other features, those are independent features. If I change one and that change is causing a change in one more independent feature, that would be a multicollinearity issue. This would be a big problem in multiple linear regression, and it is pretty common. So how to find out if you have a multicollinear problem or not? In data frame, you have something called as data frame.correlation. So what this matrix would do is, you would get a matrix. Let us say you have x1, x2, and x3. It would try to find out the correlation of x1 with other features. So it will find out x1 with x1, you'll have one correlation because they're totally same. X2 and x2 will have one correlation. They're totally same. Similarly, x3 and x3, you'll have one correlation. Now, if you find any values closer to 1 or -1 here, then it is a big problem. Why it is a big problem? Because you never know what is causing what, and the betas that you try to achieve by using this kind of a relationship would be unreliable. So always make sure that when we try to come up with a multilinear regression, check for correlation amongst the independent features. Okay, just keep this in mind. Whatever we discussed in the previous session all holds good. We should have a linear relationship. The error terms should be pretty much random. The error term should be homoscedastic, and the error term should be uniformly distributed on a QQ plot, quartile plot. All this holds good for linear regression. On top of it, when you have more than one feature, it is always important for you to go and check what is the correlation amongst my independent features. The relationship between independent feature and dependent feature is always healthy, but the relationship between independent feature and independent feature is not at all healthy. It means that x1 and x2 should not be correlated at all. When I go and check my correlation for x1 and x2, it should be very close to 0.2, or if it is 0, it is very good. Anything beyond 0.6 or 0.7 would not be good for the model, because again, because of the causation problems, the betas which you are going to find out, they would be unreliable. So speaking of which, what I'll do is I'll try to come up with one simple Excel exercise. So I'll show you one Excel exercise. Let me just find out. Give me a minute while I pull that. Right. Sorry for the delay. Right. Let us say that we have a simple data set like this, wherein my x is this, and obviously my y is, I'm just trying to calculate y by this linear equation. 2 times my x minus 1. So my model should come up with this coefficient. So my beta 1 should be 2 and my beta naught should be minus 1. So how to build a model is simple. In Excel, like you have something called as data analysis. In data analysis, you go and choose regression. So you must be having a regression somewhere. Yeah, regression. Click OK and input your Y range. So my Y range is this. Input X range. My X range is this. And then go and say I have labels. I want the output to be in the same sheet. E2. And let us go and build a model. Now, if you notice, this is a simple linear regression that we discussed in the last session. Of course, we'll also look at a Python demo, so don't worry about this. So what I want to show you is the equation which we have entered here, 2 times my x plus intercept, that is what you have received. 2 times my x plus minus 1 intercept. So the equation would be y hat equal to 2 into x plus our intercept is minus 1. Of course, plus into minus would become minus, and the equation would be 2x minus 1. That is what we have considered here, 2x minus 1. So the linear model was able to get the coefficients. Now, why am I showing this? Is for you to find out a couple of things. We discussed about hypothesis, and this is what the hypothesis says. The p-value is far below 0.05. So this beta 2 is statistically proven. It is good for the model. Similarly, the model is also having some f statistic, which is also quite lesser than 0.05. Okay, so here also we see that the model is significant, the beta 1 is significant, and the beta naught is also significant. Similarly, we can go and deal with a multiple linear regression. Now in this case, I have weekly riders, which is my target column, and then we have price per week, average parking per month, population of the city, and income of riders. Generally, because we are talking about multiple linear regression, look at the variance in the data. Okay, now let us say if I show you my if I show you this particular columns where the monthly income is about 4-digit or maybe max up to 5-digit. So we have 5-digit in income, only 2-digit or max 3-digit in monthly parking per month, and population of city is quite big. How to compare? How do you compare when there is a scaling issue in the data set? We simply have to convert this to standard scalar. So what do you do in standard scalar is you take the value xi, you separate it from its mean x bar and divide it by the standard deviation of that. So what happens when you divide by standard deviation is you get all the values between -3 to +3. And if you remember from our previous sessions that we discussed, the standard deviation, this is called as a standard deviation, or you can, once you have the standard deviation, you do not have any units to it. So let us say this x is about weight. Okay, so kg minus kg by kg. The units will remain same. Kg minus kg will still be kg. And because you're dividing by kg, this units and this units will get cancelled. Similarly, this standard scalar would apply to all continuous features. So wherever we have continuous features, all of them will get closer to -3 to +3 kind of a range, and none of them will have any units to it. So what would happen? You can go and compare units like numbers to kgs or liters to kilometers or height to weight. How to compare? Because we never know what is the relationship between 5 kilos and 5 numbers. We never know. They're not equal. And how to gauge them? Say 5 kilo of onions to 5 numbers of onions, completely different. Or let us say 5 kilo of almonds is completely different from 5 numbers of almonds. So how do you gauge the relationship between numbers and kgs? Is simply by following this standard scalar rule. Whenever you find continuous data, it is always good for you to get that data into same scale. When I say get that data into same scale, all the independent features should be of same scale. That is why it is very good for you to do a standard scalar on a continuous data. So once you have a continuous data like this, like all the four independent features are continuous here. So once we convert them to standard scalar, all of them will be a constant range, like -3 to +3. What is this -3 to +3? Let us say you have a uniform distribution. Your mean is at the center, 0, and 1 standard deviation away, 2 standard deviation away, 3 standard deviation away. Similarly, here it will be -3. So 95% of the data or 99% of the data is within this range. So that is why when you try to divide it, you will try to come up with similar kind of a scale. Of course, it might not be as exact as this, but more or less you can compare because all of them would be similar values. Okay, this being said, I think we can discuss this one more time when we reach to a Python demo session. But for now, just keep in mind that whenever we have a continuous variable, we have to convert them to a common range. You follow a min-max scalar or a standard scalar, it all depends upon you. But we have to make sure that all continuous features have common scale. Okay, in this case, for now, we are not doing any such thing, but only for understanding of linear regression, we are just applying some regression models in Excel. Okay, now let us say my y is this, and then my x is this. The output is at I1. I have labels, and then I'll click OK. So what would happen is you would end up getting linear regression. So when I say linear regression, you have coefficients. So we have intercept of like this, like 132, 914, and then beta naught. If you notice, we have price per week as -688, and average parking per month is like 162, and so on. So beta 1 x1, beta 2 x2, beta 3 x3, beta 4 x4, and beta naught. This is our linear regression. Now we have to look at what is the case of squared errors. Now I have r square. R square is 94. Adjusted R square is 93. Okay. This is a very important point. In the last session, I was telling you that just by looking at R square, we cannot tell the model is really good or not. Okay, now because we have more than one independent feature, we will have to consider variance from each dimension, say from x1 dimension, from x2 dimension, and x3 dimension. So when you consolidate all of them, then you will have something called as adjusted R square. But as we move forward to complicated models, we would not be using adjusted R square also. We would still look at the loss function or the error function. So when we have metric like mean squared errors or root mean squared errors, it is called as RMSE. Sorry, so it is called as RMSE, or it is called as MAPE, Okay, this is all for your continuous data. We are talking about linear regression because so these three would predominantly be used for calculating the loss. So whichever model is having the lowest MSE or lowest RMSE or lowest MAPE is the best model for us. And for some reason, if you find that the errors are quite high, it means that the data set is not pretty good, or the pre-processing that we have done is not pretty good. Okay, we'll discuss that when we go to the Python session. But for now, you imagine, we can notice that we have coefficients and intercepts, and we have p-values. Notice that though the model R square is pretty good, where we have close to 94%, the significant, the model, overall model is significant. It is less than 0.05. Okay, but there are a couple of p values which are not in control. Let us say the p value here for population of city is 0.56. It is not less than 0.05. So this population is not significant for the model. Okay, that is why it is having lowest beta. And similarly for income riders, we here also the income of riders is not pretty much significant. It is having 0.23. So these are the common issues that we find in multiple linear regression. So just try to convert this to a better scale, or maybe not having this in the model at all put together. So we can use the stepwise AIC function to figure out if we can just look at price per week and average parking per month to make the model or not, and then try to add one feature of population of city and one feature of riders, and see if if the loss is increasing or not, or decreasing, and so on. Okay, this is one way. Now let us come to a point. Now let us go to one area where we discussed about multicularity issue. Okay. Now I have a data set like this. Now what is my data set? I have x1, I have x2, and my y is dependent on x, both x1 and x2. Now first let us discuss about x1 and x2. x1 and x2 are having a correlation. Now what is a correlation? My x2 is 2 times x1. So if I go and calculate my correlation, how to calculate correlation is CORREL. You pass the independent features to it, comma. So the correlation is 1. There's a perfect correlation between independent features x1 and x2. Now what happens if I go and build a linear regression model on top of this? Now, okay, notice my y. I have a y equation like 2 times my x1 minus 1 time my x2 plus c. Okay, so in this case 2 times a3 minus 3 times b3 minus 1. My intercept is minus 1. Let us go and build a linear regression model now. So again, I'll go to data. I'll go to data analysis. Just in case if you do not see a data analysis tab in your Excel, you will have to go to add-ins and install the analysis pack. Okay, maybe you can find that in Google. You can, it's very easy. It's just have to install the data and then you'll find this data analysis. And then I'll click on regression. I'll choose my y. My y here is this. And then we will choose our x1, x2. x1, x2 is this. And then I'll say labels, it's not required, labels is required, okay. And then I'll say just go and put it in F2. Then I'll click OK. Now let us see what the data has to say. So when there is very high collinearity amongst the independent features, the beta knots are unreliable. See, the model completely excluded x1, and it says I can build a model with x2, and x2 is having a relationship with x1 like 2 into x1. That is what the model says. So if there is multicollinearity amongst the independent features, the model becomes unreliable and you do not get proper p-values. Okay, so we will have to first deal with multicollinearity with amongst the independent features. Only then we have to go to the multiple linear regression model. So just keep in mind, though we have spent a lot of time discussing linear regression, there are only a couple of things that we have to keep in mind. Okay, again, I want to reiterate what we have been discussing so far. We should notice that there is a linear relationship between our dependent feature y and independent features x1, x2, and so on. Our y should be uniformly distributed. Okay, y should be uniformly distributed. First is the linear equation, linear relationship. Your target should be uniformly distributed. The errors y minus y hat, okay, this is called as your errors, should be random. So when you go and plot it, you should see some randomness in the data like this, but you should not have any pattern of this kind. Okay, when you have pattern like this, you should go for time series, and then it should be homoscedastic. When I say homoscedastic, you should not have any outliers in the data, or the errors, significant errors. You should not find any errors beyond the area, like this case, like this is the outlier. So it should be homoscedastic. Okay, and the last thing is your quartile plot of your errors should be uniformly distributed. You'll find a straight line, quartile plot. Okay, this is what we discussed. And in addition to this, one new thing that we discussed today was there should be no correlation amongst the independent features. When I say independent features, they are truly independent. You should not have any correlation amongst those features. Now, what if there is correlation? What to do? You cannot say that correlation will not be there. Of course, we are talking about some real data, and real data is, if there is a relationship, there is a relationship. How to do, what to do with that relationship? How to overcome that? One thing to notice is we should be looking at the causation issue. Like, let us say if you know what is causing what, then you keep the source and delete the dependent feature. Okay, but if you do not know what is causing what, then you will have to come up with some other pre-processing steps. So one of them is variation inflation factor. So whenever there is more number of dimensions, okay, whenever there is more number of dimensions, x1, x2, and x3, and so on, xn, we go and find out variation inflation factor for all these variables. Just to keep in mind, let us say that x1 and x2 are having very high correlation, 0.95, for example. Now, what would happen if I have a 0.95 correlation and I keep it in R square? So 1 minus 0.95. And then this would become 1 minus 0.05. So this would become a very big number. So indirectly, what you're trying to do, if there is a correlation, your VIF score will be very high. This will go to the extreme level. If there is no correlation, let us say your R square is 0.01. Okay. Now what would happen? 1 minus 0.01. So 1 minus 0.99. This would be very close to 1. So generally, when you calculate the variation inflation factor for all these features, anything that is beyond 5 should be deleted. It should not be considered for making a model. Just keep that in mind. So we are talking about n-dimensional space wherein you have n independent features, and you notice for each feature there is some VIF score. Say for this one you got 2, this one you got 4, this one got 10, maybe this one got 15, and so on. So wherever the number is greater than 5, all those variables will be removed. This is one possible way. Again, we have libraries to use, so we'll directly make use of those libraries, but we should be confident in theoretical way. If you know what is going to happen, you can simply look for the code and apply it. Okay, but you should know what is variation inflation factor and when it should be used. So whenever there is multicollinearity in the independent features, try to use variation inflation factor, find out those features where the VIF score is greater than 5, remove them from the model and make a model. Okay, this is one way. And what is the other way? We also have other possibilities. Like, just in case if the VIF doesn't work, we can try out let us say that we have two features x1 and x2. Randomly delete one of them. Make a model with just x1. Let us say we have features like x1, x2, and x3. Now x1 is x2 is getting correlated. I'll try to make a model with x1 and x3. I'll calculate my S of sum of squared errors. I'll get something. Then I'll try to make a model with x2 and x3. Then I'll get my SSC. Again, I'll try to find out which model is having the lowest score. And whichever is having the lowest score, I'll try to make that as a final model. And I'll keep this out of my model building. Of course, just noticing sum of squared errors is not sufficient. Now, there are many other things that we are doing. Okay, when we are trying to make a model, you have a big data set like this. You will take, say, 80% for training. And then this is for your test. Let us say it performed well here, it performed well here. Now, how can we identify that this score is really good or it is just by chance? So there is something called as k-fold. So again, I'll try to take some more training data samples, randomly choose a different set of training samples, different set of test samples. Again, I'll run my score. I just want to make sure that the model is robust or not. So just by looking at SSC, I cannot decide. I will have to see if my model is really robust or not. My model should be robust. When I say robust, for a slightest change in data, my model should not be very shaky. The feature, the output should not vary too much. So it should be robust. When I say robust, it should not, even if there is a slightest change in my dependent features, the test result should still be it should still be looking good. Okay, so we discussed so far that we will be applying VIF, and on top of it, after applying VIF, we will be looking at trying to delete one of the features of x1 and x2, and then we'll try to delete the model. Other than this, we have something called as principal component analysis. Now, this is one feature which is very important, wherein what the principal component analysis would be doing is it would be taking all your independent features. Okay, let us say this is my independent feature and this is my dependent feature. Now, this is like x1, xn, this is my y. In principal component analysis, it will not be looking at y. It will only be looking at all the independent features. That is why it is called as unsupervised dimensionality reduction. So what it is doing, it is trying to represent this data of n dimension to a new dimension of, let us say, n minus k. This k can be anything greater than 1. So let us say if you have 10 columns and you want to represent this 10 columns as 8 columns, then you can go with PCA, which is called as unsupervised dimensionality reduction. What it does is it simply, whatever variance that this 10 columns is having, it will try to represent this variance by using 8 columns. Mathematically, let us say that we have two features. Okay, just stop sharing once. 1 minute. I'll share one more time. Okay, now let us say that we have two features, x1 and x2. Okay, I'm talking about principal component analysis. Okay, we have two features. There is some variance on x dimension and there is some variance in x2 dimension. Okay, variance is present in both the dimensions. Now what we're trying to do is we are trying to reduce the dimension in one feature and increase the variance in another feature. So if you have a square like this, let us say this is my x1, this is my x2, and the variance is present in both directions. Okay, the variance is present in both directions. Now what will happen is, by using PCA, you'll try to reduce the variance of one dimension. So let us say if I reduce the variance in one dimension, I would have something of a stretch. The square here has been stretched and your center is here. So the the variance present in x2 is reduced and the variance present in x1 is increased. Okay, you might not have understood what I said. We discussed this previously. When there is no relationship between my y and x, this is my y. When there is no relationship between my y and x, the slope is equal to 0. Agree or not? We discussed this. There is no relationship. The correlation is 0. The slope is 0. And we should be able to predict y just by using the intercept. Okay, we don't need x. Irrespective of whatever my x is, my y is not going to change. So indirectly, what you're trying to do, you're trying to make the slope as 0. Similarly, in PCA, for x2 dimension, I'm making the slope as 0. In order to make the slope of x2 as 0, I have to make some changes in x1. The beta of x1 is changing. The variance of x1 is slightly variating. So this square is now stretched on one direction. It's stretched in this direction. It reduced in this direction. This is what the principal component analysis is doing. The effect of one feature is completely reduced. Conversely, the same effect is increased in one more feature. So x1 and x2 are now signified as xk or maybe x3. Now, what is the relationship of this x3 in terms of x1, x2? We do not know. Maybe by using mathematics, you can find out. There is something called as eigenvalues, eigenvalue and vector and maybe matrix. So using these concepts, we can go and find out the actual relationships. But when you look at the numbers, we definitely cannot tell what is the relationship between x1, x2 and x3. Okay. So what is happening is when we had to make a model with x1, x2, we used principal component analysis. We represented this x1, x2 as x3, and now we are making a model based on x3. This is what principal component analysis is doing. Of course, we'll have a session on this, but for now, just keep in mind that when we have more number of features, there is a possibility of multi-collinearity amongst the independent features. And when there is multi-collinearity in the independent features, we have to go with VIF or PCA, or just randomly delete one of the features and try to build a model. Okay. Now, just one more thing before I stop today's session. Let us say that we have a measurement on sum of squared errors, like the coefficient of determination R square, and the R square for a given model is 94. Okay. For achieving this 94, let us say I considered about 10 features, 10 of my independent features. Okay. Now let us say if you can achieve the same 94 with 7 features, this would be a simpler model, and this would be a complicated model. As I increase my independent features, the complexity also increases. More the number of independent features, higher the complexity. Lesser the number of independent features, simpler the model, provided you have the same metric. Now, by using 7 of my independent features, if I say that I'm going to get 93, then I cannot compare 94 and 93. It is not good. Keeping the same error metric, if I can achieve the same error metric with lesser number of independent features, that should be our chosen model. Okay, this is called as Occam's razor law. Simpler model is a best model, but provided you should always note that the error metric should remain same. It should not be like because I said simpler model, I'll go and build a model with 5 independent features and it is giving me 90 R square. No, that is not good. Okay, keeping R square in mind, at a constant R square, if you can come up with a lesser number of features, then that should be our simpler model. Okay, just before I break for today's session, just in today's session, what we discussed was, again, when we have more than one features, we should be able to calculate y hat with some kind of a equation like this. And when we have an equation like this, the common issues that we find is multicollinearity. So how to deal with multicollinearity is by using VIF, or you can go with stepwise AIC function, or we can go with PCA, and we can also go randomly go and delete feature. This is what we discussed so far. Okay, that is all with multiple linear regression. Of course, we'll have some more discussions around this. We'll understand what is overfitting, what is underfitting, what is high variance or high bias. We'll be discussing all this in the next session. So stay tuned for more. Thank you so much.